Hello everybody, and welcome to the next lecture of 6838. Today we're going to continue our discussion of inverse problems where we're given distance values as input and our job is to reconstruct an embedding. But now, rather than reconstructing an embedding given like every possible pairwise distance between every pair of points, we're going to consider a variation of the problem where maybe what we care about more is only preserving local structure. Here, the idea is that maybe we don't really care about things that are far away. We just want to make sure that relationships between things that are nearby are preserved. And this is a pretty common structure to have. So for instance, we've already talked a lot about tangent planes, curvature, and so on when we discussed manifold. Remember that all of those kinds of constructions are basically very local, right? They just involve a point and some small neighborhood around that point in a manifold. And so it might be the case that what we really care about is preserving that kind of manifold structure more than preserving distances between things that are really, really far apart. So to put it differently, essentially what we want to do in this lecture is to consider a slight change in perspective. So in the previous lecture, when we talked about the MDS algorithm and stress majorization, we were essentially describing a picture that kind of looks like what I'm showing you on the left, right? This is the idea of extrinsic embedding, where essentially all distances between all points are roughly equally important, right? So remember that in our previous lecture, all of the algorithms we described were given a n-squared sized pairwise distance matrix D, and then we were trying to find an embedding from that. But oftentimes, what we find in data analysis is that local information is more reliable than global. So for instance, in this collection of points, maybe I collect the k nearest neighbors for our points, and what I receive back is some graph that looks like the one we see on the right-hand side. Now, on the left-hand side, if we're given the length of every one of these n-squared line segments, and we try to embed it, this shape is going to be very clearly planar, right? It's going to require 2 dimensions to embed all of those distance values well. But if you look on the right, well, here, for example, we could unhinge this chain of line segments and embed this object into a straight line while preserving most of our pairwise distances. So now, essentially, by only prioritizing local distances, we can sometimes get a lower dimensional embedding of our data than when we require the whole thing on the left-hand side. In fact, there's a lot of theory about this as well. For example, if you read about rigidity theory, which deals with the case of sort of hard constraints on this problem, essentially one way to look at the picture that I've drawn you on this slide is that the left configuration, if we were to construct it out of toothpicks with like one toothpick per red edge here, the left configuration would be rigid, right? Whereas the right configuration, constructed out of toothpicks, is flexible, right? I can hinge each of those vertices around. And so that additional flexibility oftentimes can buy us different types of embeddings and ones that preserve different types of structure that might be more important for a given data analysis problem. Now, in principle, it turns out that these problems are definitely linked. Now, citing a theorem like this to justify the algorithms we're going to talk about is a little goofy. I mean, the Nash and Whitney embedding theorems are really, really strong sledgehammers and totally theoretical objects. But they're also crowning results in geometry, so they're worth mentioning. The basic point here is that if we have any Riemannian manifold structure, which is basically a weaker structure than the embedded submanifold structure that we developed a few lectures ago, if it is intrinsically k-dimensional, then we can actually map it smoothly into r to the 2k. And in fact, the really amazing result from Nash and some follow-up work that simplified it and so on, even asserts that a k-dimensional manifold can be embedded into 2k-dimensional space in an isometric fashion, which is pretty amazing. Now, you might wonder what those isometric embeddings look like, and the reality is that they're really, really complicated. So for example, here we have the Nash embedding of a flat torus, and it creates this like totally ruffled up object, which really computationally we couldn't work with. So, you know, the reality is that although the problem of intrinsic and extrinsic embedding are definitely linked in some fashion, the link is not super clear, and it's not always played out in algorithms. Incidentally, one thing to notice is that these theorems are still dealing with geodesic distances, right? So when they say that this is an embedding of a flat torus, what they mean is into like a two-dimensional surface embedded into some space where the intrinsic dimension, the intrinsic geodesic distances along the surface are the things that we're embedding. It's not like cutting across in space. That would be a different problem. So this is just a weak theorem that's only coarsely linked to the problem that I laid out, but I figured I'd mention it, and you guys should Google and read about these famous results in mathematics. But in any event, embedding things from a practical perspective has been around as a problem for a very long time. And there are many different algorithms out there, including many that are quite popular in the data science community. So the first one that I'll mention is basically an extension of the MDS algorithm that we talked about before. So remember what the MDS algorithm does. It takes the pairwise distance matrix where, for every pair of points, we know the distance we'd like between that pair of points in our embedding. And then just using an eigenvalue problem, it recovers an embedding of that pairwise distance matrix into Euclidean space. And if we clip the eigenvalues at smaller and smaller dimensionalities, then now our embedding becomes approximate, but it still provides kind of a useful output. We also had a nonlinear variant of this, if you recall, which we called stress majorization, which essentially took the same output, like a pairwise distance matrix, and then gave us back an embedding. Now, there's a very simple extension of either of those two strategies, which leads to a method that says, maybe I don't care about the extrinsic structure associated to a given geometric domain, but rather just the intrinsic structure, like the local distances between points. Now, the classic data set that everybody uses to study this problem is called the Swiss roll data set, and that is shown at the bottom of the slide here. Now, the Swiss roll data set is named after a pastry called the Swiss roll, where you take a piece of cake, which is very thin and wide, and you wrap it up like this. So it makes this sort of spirally shape embedded in 3D. Now, because it's a data set, we don't have a triangle mesh or anything, but rather it's just a collection of points that's concentrated on this rolled up piece of cake here. And now the Swiss roll data set is really clearly intrinsically two-dimensional, right? It looks like a surface, but it's embedded in 3D, and because it's just a big cloud of points, we forgot that. Now, if you took the pairwise 3D distances between every pair of points, like what's shown on the left image here, and you tried to embed it using MDS, you would get three very non-zero eigenvalues, right? Because looking at this Swiss roll dataset globally, there's very clearly three-dimensional structure. But if I only care about the relationships between points and other points that are nearby, for example, in the middle image here, then it becomes easier to embed this object into the plane, essentially taking that Swiss roll and unfurling it into a two-dimensional rectangle. Now, how does the Isomap algorithm do this in practice? Well, it's actually quite straightforward. It basically just adds one step to the MDS algorithm, which is our first well, I've taken this step and broken it into two bullets on the slide here. So the basic point in Isomap is that you first construct something called a k nearest neighbor graph, or something related called an epsilon neighborhood graph. These are really simple graphs on our input point cloud. So we're given as input a data set like these points on this Swiss roll object. And now the k nearest neighbor graph, what it does is every point finds the k closest points to it in the data set, and that forms a graph where there's an edge from every point to its k nearest neighbors. The epsilon neighborhood graph does something similar, but rather than collecting k nearest neighbors, it just adds an edge between every pair of vertices within distance epsilon. But the basic point is that the edges in this graph, if you look really carefully in this middle image, you'll see that they're illustrated in gray, are essentially giving some notion of like almost a tangent plane or a local neighborhood for every vertex. So in the Isomap algorithm, the first step is to construct this graph. Then the second step is to construct a pairwise distance matrix, and this is where all the magic happens. Now, when we motivated the MDS algorithm in our previous lecture, we assumed that our pairwise distance matrix was secretly computed as pairwise distances between pairs of points in Euclidean space. Isomap kind of is a little bit of a hack there. So what it does is instead it computes the pairwise distance matrix between every pair of points in our data set, like our Swiss roll data set. But rather than computing those as distances just in 3D space, we compute the distances as shortest paths along the graph that we just constructed. Right? So for example, the shortest path between two data points on the Swiss roll data set is shown in the middle image here. And again, this is just the shortest path on the k-nearest neighbor graph. But in any event, now we have pairwise distances between every pair of points. We can compute them using Floyd-Warshall algorithm, Dijkstra's algorithm, or many other techniques, Bellman-Ford. Then after we have that matrix, well, now we can just follow MDS or stress majorization or whatever your favorite extrinsic method is to try and embed that pairwise graph distance matrix. And what you'll get is an embedding like the right-hand side. So the basic magic in Isomap is basically a pre-processing step for MDS, right? All it does is define kind of a clever source of a pairwise distance matrix that isn't Euclidean, but rather comes from a graph. Incidentally, many of you are probably familiar with a particular technique, which is like 4 lines of code for getting the pairwise distance between every pair of vertices on a graph called Floyd-Warshall. This is basically just a magic trick for updating the triangle inequality a bunch of times and convincing yourself that you get the shortest pairwise distance. This runs in n³ time. We're not going to cover it in this course because it's sort of a basic algorithm, but this is just a useful Google search term if you want to implement Isomap on your own. It's also worth mentioning that just the same as we talked about a landmark version of MDS, we can essentially apply that lambda MDS technique that we already derived to deriving a landmark Isomap algorithm. So remember, in landmark MDS, when we introduce a new point in our data set, we just need sort of the vector of squared distances to all the old points. So now in landmark Isomap, what we do is if we have a new data point, we add it to our k-nearest neighbor graph, compute its distance to all the other points, for example, using Dijkstra's algorithm. That gives us that vector that we need, and now we can compute our embedding directly. So again, the Isomap algorithm is really straightforward. All it does is replace the input matrix to MDS with one that we got by computing shortest paths on a graph. Let's take a quick pause, and then we'll continue. Okay, so basically every time almost any course in this area of research covers the Isomap algorithm, the very next thing that is covered is a different algorithm that was proposed roughly the same time and has very similar application. But the math and the construction is quite different, so I think it's worth mentioning. And that is a technique called LLE, or locally linear embedding. So almost always you hear people in the same breath say like Isomap and LLE. But in any event, LLE algorithm is trying to maintain a very different structure. The basic point in the LLE algorithm is to use the fact that oftentimes I can take a point in my data set, remove it from the data set, and then write that point as a weighted average of other points in that data set. That sounded a little bit complicated, but it's actually not so hard to think about. So in particular, again, like let's say that I have some data set, you know, I guess I need to draw these points in a big fashion. Here's my data set. This is 2-dimensional. Obviously, it's on the plane of my whiteboard. I can take some data point, for example, this one right here, remove it from my data set, and actually still write it as some weighted average of points nearby. And the basic idea of the LLE algorithm is to preserve this little structure in an embedding, right? So for example, in that Swiss roll data set, this is still kind of true, right? Because if I have this planar object, I'm going to get in trouble trying to draw it, whatever. If I have some point on my Swiss roll, and the Swiss roll is itself sort of densely enough sampled, then even though the Swiss roll doesn't fill up all of 3-dimensional space, notice that like I can still take points and just kind of grab their k-nearest neighbors and write them as a reasonable average. And in some sense, this is just some observation about the tangent plane of our manifold. So the LLE algorithm happens in 3 steps, 2 steps, depending on how you do your accounting. So the first step is identical to Isomap. You compute a k-nearest neighbor graph or an epsilon neighborhood graph. Either one will work. And that's exactly the same as before. Now we have two kind of key numerical things that we do. The first one is called an analysis step, where what we're going to do is compute weights wij, so that essentially we're going to take every vertex and write it as a weighted average of some nearby neighbors in the k-nearest neighbor graph by solving a least squares problem. And then in an embedding step, we're going to take those weights, throw away the original data set, and try to find a new lower dimensional data set that satisfies a similar property. So in other words, when I unwrap my Swiss roll into the plane, I want that the unwrapped points are roughly the same weighted average of their neighbors that I had in the original 3D data set. So let's derive the analysis step and the embedding step in a little bit more detail. Okay, so we'll move it into the corner here. So the first thing that we have to do is write down the analysis step. Analysis step. Okay, so what we want is that we want to write each xi as a weighted average of its neighbors in the k-nearest neighbor graph. So just to add a little bit of notation here, let's call its neighbors, let's give them a name, we'll call them n sub j, which is essentially just some subset of my entire data set, which I've gotten from my k-nearest neighbor graph, right? So I have each vertex xi, so I have a big for loop over those, and for each one of those, I'm going to gather a collection of neighbors nj, which are all the neighbors in the k-nearest neighbors graph, which is just some subset of the data set. Okay, so essentially the way that we're going to do this is we're going to have an unknown vector, omega, and we'll have a few properties of omega that we want it to satisfy. So first of all, we want, and by the way, there's one omega for each xi. So we're going to write down the problem just for a single data point xi. And for now, I'm going to drop that I subscript to be a little bit lazy. Okay, so what we want is that xi is roughly the weighted average of its neighbors, meaning that if w's are the averaging weights, then we want something like that. Okay, but because they're averaging weights, we additionally want a second property, which is that they sum to 1. Okay, so this is what we want. And the question is, how can we get it? Well, as with most problems in this class, the best way to try and compute things, given a bunch of properties, is to write down some optimization problem and try and solve it. So in particular, this leads us to an optimization problem that looks like the following. So essentially, we're going to have the min over vectors w of the following, or omega, I suppose, xi minus the sum over j of wj nj. Right, so this is just saying I want the vertex xi to be a weighted average of the nj's, right? This norm is 0 when that's exactly true. But we have a constraint, which is that the sum over j of the omega j's is equal to 1, because otherwise they wouldn't be averaging weights. So if we write down the KKT conditions, like if you go back to lecture 2 of this course, you'll see that we actually already wrote down how to solve least squares problems like this. If you don't remember, might I suggest doing a quick calculus Lagrange multiplier review? But essentially, what you're going to end up finding is that you satisfy the following linear system. So for one, we can write down n to be the matrix of neighbors, right? n1, n2, and so on, like that. We already have that omega is a vector, right? So for instance, this constraint here is the same as saying that the vector of all ones dot product with omega is equal to 1. If we want to be slick about it. And up here, we can write this least squares problem as xi minus n times omega, right? That would be the nice vectorized way to write it. So given all of that, what we're going to end up with is n transpose n, the vector of all ones, transpose, and 0 times omega lambda equals n transpose xi and 1. Okay. So this is just the KKT conditions for this optimization problem. I keep saying KKT condition, really just the Lagrange multiplier condition. And notice that it almost looks like the normal equations, right? Like n transpose n w equals n transpose xi. But we need one additional thing to cope with the constraint. Notice that the constraint here is just 1 transpose omega equals 1, right? That's what this second row is saying. So it's not all that surprising that these are the KKT conditions. So in practice, what happens in the analysis step of LLE? Well, we loop over every single one of our xi's here. We gather its neighbors nj from our k-nearest neighbor graph, and then we solve this linear system of equations. By the way, if you use the k-nearest neighbor graph, it's kind of nice because essentially that gives you a bound on the size of this matrix, right? It'll be k plus 1 by k plus 1, which somehow makes your parallelization a little easier in your code. And then once you do that, what you get is a different vector omega for every single one of our vertices, with the property that omega is basically a weight associated to that vertex and its neighbors. By the way, we typically assume that there's no self loop here, right? There's not like a weight for yourself, because obviously then you'd put 100% of the weight there and 0 everywhere else. Right. So, by the way, if you do some dimension counting here, you can kind of figure out the number of neighbors that you want to collect to make this least squares problem well posed, or if you grab too many, it might end up being underdetermined and you have to regularize. But those are essentially just some implementation details. Okay, so we're going to write a matrix form of the omegas as follows. We're going to say, we're going to write a matrix W. I'll try to be careful with my subscript here. N J here. So essentially the point is, this is actually really sloppy notation, but hopefully you guys are going to be okay with it. I'm going to make a matrix which is indexed by every vertex and every neighbor, which is just equal to, this should be omega j. The idea that, like, after I loop over every vertex, I collect its vector and I put it into this matrix. The reason why this is bad notation, this is a vector of length equal to the number of neighbors. This is really the total size of the data set squared, but I'm thinking of it as a sparse matrix with non-zero entries only when you have a neighbor. So anyway, I should probably just preface that this notation is more annoying, more complicated than it needs to be. But in any event, the point here is that I get this matrix W. That's the main output of the analysis step of LLE, and every row of W is non-zero corresponding to the set of k nearest neighbors for that vertex. And the row sums up to 1 and gives us averaging weights computed using this problem here. Okay, so anyway, that's the whole point. We can ignore everything on the bottom of our board here and say, okay, the analysis step iterates over every xi and does so to construct this weight matrix W. So the next step that we need is the synthesis step, or the embedding step. So let me erase the board so we have some space, and then we'll derive that. Okay, so our next task is to derive the embedding step of the LLE algorithm. And now the basic point here, we just derived this matrix W when we were doing the analysis step. And W has a particular property. So if I take all of my data points and I write them as the column of a matrix X, then essentially the whole point of the design of W is that I can write x equals x times W transpose, at least approximately. What's the idea here? Well, when I take x and I post-multiply it by W transpose, what I can convince myself is that this is basically like computing the weighted averages for each of the rows for each data point that we had as input. And the entire point of computing that W was to make these two things look close to one another. So essentially what we're going to want is an embedding Y, and Y is going to be a matrix with the same number of data points. So we're going to say there's n data points. And if this problem is in m dimensions as input, well, then what do we know? We know that x, we can say, is in Rm by n. So our output, matrix Y, what we're going to ask for is that this is in Rp by n, where p is hopefully a lot less than our original dimensionality. Okay, and how are we going to compute Y? Well, we'd like exactly the same relationship, namely that Y is roughly equal to Y times W transpose. Now here's a problem. Is this condition sufficient to make for an interesting optimization problem? So for example, we can say, okay, well, I'm just going to constrain the size of Y to be P by N, and I could write the following optimization problem, which is to minimize Y, the norm of, I guess, Y minus Y, YW transpose, like that. This would be the Frobenius norm. Well, if you think about it for a second, if you think about it for 2 seconds, the first second you spend understanding that this thing I wrote here is supposed to be a Y, then essentially what you can convince yourself is that this is not an interesting optimization problem because it just leads to Y equals 0, right? If I put in Y equals 0, I get, well, then it's absolutely true that Y equals Y times W transpose. That's just Y times 0. 0 times 0 equals 0. So instead, in LLE, we add a constraint. Namely, we write that Y times Y transpose is equal to the identity matrix. So the basic point here is that now we're going to ask that there's some kind of orthogonality condition which is making sure that our embedding is non-trivial, right? Like there's no way I could get the ones down the diagonal of the identity matrix if Y were equal to 0. Moreover, shifting our data doesn't do anything interesting, so we'll also add a constraint that the data points sum to 0. This is just like we had last time. Okay, so essentially, if we combine all these things together, what we're going to get is just an eigenvalue problem. How do we see that? Well, for one, okay, so the inside of this Frobenius norm can be written in a slightly nicer way, which is Y times identity minus W transpose, right? Already this is a little bit nicer than where we started. And right, so let's go from there. So okay, if we work out the trace here, we can use a trace norm identity for the Frobenius norm. So we have, well, our objective function is Y times the identity minus W transpose. As usual, by the way, I'm sensing that I'm already making a mistake. I'm not 100% sure whether this should be transposed or not, but you guys are all graduate students in computer science, so I think you can go back and check later. But anyway, assuming that there is a transpose here, the way we can write this problem, remember that in general, the Frobenius norm of a matrix squared can be written as the trace of that matrix times its transpose. Okay, so in particular, what do we get? We get that this is the trace of Y times identity minus W transpose times identity minus W, assuming that W isn't symmetric. By the way, we do expect W to be roughly symmetric because of how we got the averaging weights, but that doesn't really matter here. Okay, So let's see, with a transpose here. Did I do that right? Y. Yeah, that looks right. Okay. So, okay, we can expand the square in this expression here. And we're not going to get anything terribly exciting. It'll be I minus W transpose minus W plus W transpose W. By the way, if I got my transpose wrong, this is the term that would be different, right? It would be WW transpose. I'm going to let you check the course notes or check that at home. But in any event, what we're going to do, because I'm bad at math, is we're just going to give this thing a name, and we'll call it M. Okay? So if we factor M out, then essentially our optimization problem becomes the following. It becomes minimize the trace of Y M Y transpose such that y transpose equals the identity, and y times the vector of all ones equals 0. And from here, I'm going to let you guys work out. For one, it's easy to see that M is a symmetric matrix. And essentially, because M is a symmetric matrix, what you're going to find if you work through the optimality conditions is that essentially the way that I'm going to obtain my, my matrix Y here is just as the matrix of the top P eigenvectors of M. Or I'm sorry, it's not the top P eigenvectors in this case. It's the bottom ones because this is a min, right? So this is the bottom P eigenvectors of M. So I'll leave it to you guys to do the Lagrange multipliers to get from the left to the right-hand side here. But it's a really straightforward argument. Notice that because M is symmetric, assuming that there's no repeated eigenvalues, which generically is going to be true, the eigenvectors of M already satisfy the first constraint because eigenvectors are orthogonal when they correspond to different eigenvalues. And we can take care of the second one by making sure that it's the bottom P eigenvectors of M, comma, with non-zero eigenvalue. So if you're unconfident why you can glance at the problem on the left and immediately get to the problem on the right, I would encourage you to basically take a very close look at essentially the argument in the course notes or derive it yourself, because this is a really basic fact. The only slight twist here is this constraint, but we'll see that because we constructed our weights W carefully to always sum to the same value, to 1, the second constraint is not so hard to satisfy. And even if you forgot that, you could write down a different eigenvalue problem that's pretty close, where you essentially just project this space out of M before computing the eigenvectors. So in any event, from a high level, even if, as usual, I likely messed up the details of our calculations a little bit, the basic point here is as follows. Remember that we have these 2 steps in the LLE algorithm. The first thing that we do is construct a matrix W with the property that it's giving us averaging weights, where we're saying that essentially every row or column of W is telling us, either row or column, I'd have to think about it, is basically telling us the averaging weights to approximate each data point with some set of data points nearby. And then in the embedding step of LLE, we say, okay, well, by construction, we have this relationship about X, and this is just an expression about how we wrote it down. And now, essentially, we're going to compute a Y and ask that Y satisfies the same approximate relationship, but we're going to force Y to have fewer rows. And that's going to be the dimensionality of our embedding, which is P. And we get that by writing down this optimization problem here. And sneakily, by choosing the right kind of constraints, we end up with an eigenvector problem of a matrix I minus W transpose minus W plus W transpose W or WW transpose, whichever one makes sense for our choice of rows versus columns of W. I'll admit that I fudged that a little bit. But regardless, once we have this matrix M, all we're going to do is compute its eigenvalues and eigenvectors. And the ones corresponding to the lowest eigenvalues are exactly the LLE embedding. And thankfully for us, computing eigenvalues is like a one line of code, call in Python, MATLAB, whatever your favorite programming language. Phew. So at the end of the day, the LLE algorithm, it takes a little bit of math to derive, but it's really not so difficult to implement, right? So it basically takes place in a few steps. The first one is compute the k-nearest neighbor graph. The second one is to compute the weight matrix W. And the third one, oops, I even had that hiding in the slide, is to reconstruct your data by solving this optimization problem. And essentially when we do that, what we end up with is an eigenvector problem, which I think I got right. Why identity? No, I'm not going to get hung up on it while we film the lecture. But in any event, that's it. So the real question we should be asking is how do we compare these two different options, Isomap and LLE, both of which are intended to recover our Swiss roll data set basically in 2 dimensions, but get there in 2 very different ways, right? So Isomap gets there by essentially approximating the geodesic distance function in some fashion using a k-nearest neighbor graph. And LLE gets there by using some kind of tangent plane assumption and then reconstructing based on that. And in our next slide, we'll see a comparison, which we'll look at right after I erase. Okay, so let's compare these 2 techniques. We've got Isomap and LLE. So the basic points that differ between these 2 algorithms is given in this table here. So probably the biggest one is the first row of the table. That the Isomap algorithm compares the pairwise distances between every pair of points on this graph k-nearest neighbor structure, and then given that, tries to embed the entire global pairwise distance on our graph into the plane, whereas the LLE algorithm has just this local averaging relationship that it's trying to preserve. Why does that matter? Well, oftentimes what can happen in Isomap, let's say that I have my Swiss roll data set, so here's my spiral, like looking on it at the side, and by accident, I end up with just like one spurious connection like that. Well, suddenly, our k-nearest neighbors graph has this bad edge hiding here, and what can happen is that can throw off the structure of the entire k-nearest neighbor graph distance matrix, because now suddenly, the shortest path from, for example, any vertex on this entire segment to the inner part of the Swiss roll is much smaller. And so just that one spurious edge threw off the entire computation. What that means is that this algorithm can be quite sensitive to the choice of k and to the construction of the graph. But in any event, there's some other differences as well. So for example, one of them uses graph distances, the other uses graph weightings. One computes the smallest eigenvector, one computes the largest. Right? Isomap effectively computes largest eigenvectors because it's borrowing the MDS algorithm, whereas LLE, we just showed, computes the smallest ones. And then probably the third one is important computationally, which is Isomap works with a dense matrix, and LLE works with a sparse matrix. These different algorithms can have some funny byproducts that are tricky to figure out. So for example, I think probably the most clear example of what can go wrong in the Isomap algorithm is shown all the way on the right. So here they've taken a Swiss roll data set and I kind of punched a hole in the sheet. So it's like a rectangle, here's my Swiss roll unrolled. And now, we're going to cut this little piece out in our Swiss roll and roll it back up. That's the data set on the right. So if you think about what the LLE algorithm wants to do, well, suddenly there's all kinds of funny properties that happen. So for example, the shortest path from here to here, Well, thanks to the hole, it kind of runs into the rectangle and then goes into the other point. So in effect, these 2 points are farther away than they should be. So what happens when I compute the isomap embedding of this Swiss roll with a hole data set is that you end up kind of bulging out like that in the middle. So here's our Swiss roll, and the idea is that essentially what we're trying to do is capture these longer paths that have to cut through the missing data in our k-nearest neighbor graph. LLE does not have that issue, but on the other hand, it doesn't capture some of the global relationships that the k-nearest neighbor graph in Isomap does. So in any event, my advice about this, as with most algorithms we see in this course and we see multiple options, is try them all and see what works best for your data. None of these are particularly hard to use. Many of them are implemented in existing data science toolkits, so they're quite easy to experiment with. And there are many other alternatives. So one that we're going to defer on for now is something called diffusion maps, which essentially constructs a Laplacian operator and then uses that for the embedding of your data, which has to do with diffusion distances. So like how long it takes the heat to diffuse from one data point to another. But since we haven't really defined the heat equation yet, or the Laplace operator, we're going to defer on that until we have some more mathematical machinery at our disposal. Let me erase really quick. Okay. So I thought I'd also call out one topic which in a traditional geometry processing course would probably occupy at least one lecture, if not more, which is mesh or surface parameterization. This is a task that's really important in the computer graphics universe, where you take a triangulated surface, specifically one with disk topology. So this octopus is a little misleading. Somebody's punched a hole in the octopus somewhere. And your task is to map that into the plane. This is a really important problem because essentially once you've parameterized your surface into the plane, you can like store texture as an image for the surface and then display it back in 3D. And so there's a ton of geometry processing research on this problem, including some of my own. One interesting perspective that I think fits in really nicely with the algorithms that we've talked about so far for structure preserving embedding is really one that's driving many of the state-of-the-art techniques. So here I've borrowed a lot of figures from one particular popular algorithm. This is called Scalable Locally Injective Mappings, or SLIM. I've given the reference on the slide here. But the basic point here is when I map a triangle into the plane, so here's my 3D space. I can think of a triangle mesh as just a big pile of triangles, of course. And now, the task of parameterization is to take the vertices of my mesh and place them into 2D like that. And essentially when I do that, one thing that I can figure out is, okay, so how many degrees of freedom are there? Well, for a single triangle, I have to figure out where to place all 3 of its vertices into the plane. So there's 6 numbers total. So that's kind of like a 2x2 matrix plus a translation. And indeed, you can kind of approximate a Jacobian matrix from the triangle in 3D to the triangle in 2D, maybe plus, taking the direction normal to the triangle to the z-axis, like out of the plane here. And what you get is a Jacobian matrix J. So here again, J, you can think of as sort of taking a linear function, like barycentric coordinates in this triangle, and mapping it to a linear function here, and then differentiating it. In any event, if you didn't follow that, we're going to construct piecewise linear finite elements in the next couple lectures when we talk about Laplacians, so you can return to that. But the basic point here is that you can get a Jacobian of a map from a triangle mesh into the plane, and then essentially you can understand these parameterization algorithms as trying to minimize an objective like what I've shown you on the right-hand side, where you sum over all the triangles of the mesh some function of the Jacobian of the map from that triangle into the plane, maybe weighted by area, right? That's that A sub f. So here, D stands for distortion. And the reason that I think these algorithms are actually quite similar to, for example, stress majorization and some of these other techniques that we've talked about, remember that stress majorization basically constructs a graph you can think of on your data, right? Which is like the distances between all the edges, and then has this nonlinear objective function, which is trying to minimize the distortion of every pairwise distance. Mesh parameterization is trying to do something very similar, but just instead of summing over edges, right, like pairs of points and trying to make their distances the same, it instead says I want to sum over triangles and make the distortion of the triangle pretty close to the identity matrix. Right? So essentially one way to do that is to look at the eigenvalues or the singular values of J, and you want these all to be close to 1, at least those, because that corresponds to just a rigid motion. Right? And so in any event, I encourage you guys to read this Rabinovich paper and keep in mind, the perspective of, Isomap, LLE, in terms of taking, some curved object, mapping it into the plane. So here we don't need a k-nearest neighbor graph. Our graph is the triangle mesh. But now it gets coupled with these nonlinear objectives. They have this big table here, which is really convenient and fun to think about, which are kind of extensions of that stress majorization objective function just to measuring triangle distortion instead of per edge distortion. But then their algorithm is really quite simple. It's just gradient descent on the objective here, where I'm moving around the vertices of my parameterization to reduce the distortion of all the triangles. There's one key consideration that we're not going to cover in this course, which is injectivity, which is to say that if I have a parameterization of a triangle mesh and two triangles share some piece of the plane, the whole parameterization is garbage, because then my texture map ends up applying to two different parts of my triangle mesh, which is no good. And so there's some really clever techniques for coming up with bijective maps, or at least injective maps from a surface into the plane. Probably the most common ones are all built off of a line search technique proposed by Smith and Schaefer, where you come up with one initial guess of a parameterization whose distortion is really bad, but is guaranteed to at least be bijective. This is called TUT, and we'll return to the TUT embedding when we talk about the Laplace operator, but we haven't introduced that yet. And then once we have some bijective map of our object into the plane, like the initialization on the left, notice this is basically taking that whole octopus and mapping it to like a circle, so the distortion is going to be really terrible. Then it's basically just a gradient descent procedure with backtracking. So essentially every time your parameterization becomes non-injective, so like two triangles overlap, it just backtracks. Then there's some special calculations you can do to help kind of figure out when that's likely to happen. So anyway, this is a totally classical topic. In many geometry classes, this would take up many lectures, but I think you guys, it's actually a pretty straightforward literature to read, so I'm going to let you guys take a look at the mesh parameterization papers if you're interested in that kind of area. And this is one interesting one that starts with an optimization perspective. They also propose a preconditioner for optimization problems of this particular shape. Now, one thing I'm totally neglecting by talking about parameterization this way, right? So the way I've described it, you have a triangle mesh in 3D, you're placing all the triangles in the plane, and you're just summing over all the triangles some distortion measure, and that looks an awful lot like the stress majorization technique. That's absolutely true. But actually, the history of mesh parameterization, including many linear methods, is really built on conformal geometry and partial differential equation, which essentially come out of the KKT or optimality conditions of these optimization problems. So in particular, there's some kind of quadratic looking parameterization objective functions which many people use, which end up translating nicely into like Laplacian looking systems of equations, which again we'll defer to until the next couple lectures. So if none of that made sense, that's okay. This is mostly just an aside, but the basic point here is that actually the state-of-the-art methods for nonlinear mesh parameterization are really, really similar to what we've talked about for distance metric embedding. It's just that rather than summing over pairs of points, they're summing over triplets when they cook up their objective function. And with that perspective, I think these papers are actually quite easy to read. So let's erase and keep moving. Okay, now just for fun, I thought I'd call out one other research paper that I thought was doing something totally crazy and interesting. So far, we've talked about embedding in a structure-preserving way things into Euclidean space. So like just preserving local distances or something like that. One thing you might ask is, can you somehow come up with an embedding of a surface or some other object by preserving its geodesic distance function? So rather than just, basically conserving lengths of straight lines in 2D or 3D or whatever. I actually have maybe the topology of a triangle mesh, and I know the geodesic distance between every pair of points of that mesh, but I forgot its embedding, and I want to try and find it again. There's very little work that tries to modify a surface to realize a given pairwise geodesic distance function, but I thought I'd call out this one. Mostly, sometimes you read a paper and you think, oh my, like some graduate student really suffered implementing this thing. Somebody actually did manage to differentiate through the fast marching algorithm that we derived a few lectures ago in order to come up with surface embeddings whose geodesic distance rather than Euclidean distance functions are prescribed. So this would be like, given not just the edge lengths of a triangle mesh, but even the distances between distant points, trying to realize that thing, but in a way that the fast marching algorithm gives you the distances that you desire. Anyway, I'm not sure I would implement this particular technique in practice unless you have a really strong reason to, but it's kind of cool that this algorithm exists. So the takeaway from our discussion so far is that there's a huge zoo of different embedding techniques, each with different theoretical properties. Some preserve local structure, some preserve global structure, some are eigenvalue problems, some are nonlinear optimization problems. My basic advice here is to try them all. Unless you know exactly what structure is hiding in your data set, then probably it makes sense to try a couple different embedding techniques, and the ones that are successful might tell you something about the structure that you're trying to find. But of course, many of the algorithms we've derived so far essentially are assuming that we have as input some distance matrix, or at least some local distances, where the distance values that we have are pretty reliable. There are other problems and other variations of our embedding algorithms out there that, for example, try to complete extremely incomplete distance matrices or to recover from noise. And so I thought I'd just briefly call out a few more or less internet search terms that you can look into and some basic algorithms for other variations on the theme of the problems we've talked about so far. So for example, one simple problem in principle, although solving it is quite tricky, is the metric nearness problem. So this is kind of like a projection problem. It says, I'm going to take some generic matrix X and project it onto the space of distance matrices. So here, remember that a generic matrix X may not be a distance metric, right? It might not have a triangle inequality. It could have negative entries, whatever, which violates the assumptions that we've put on our input, for example, on the MDS algorithm. So one thing I might do before calling MDS is take my messy distance matrix, like maybe I run a survey and I ask people like, estimate the distance between these 2 points, and people are very unreliable, so my matrix isn't too good. The first thing I'm going to do is project it onto the cone of matrices with the triangle inequality and so on, and then run all my embedding algorithms. So this metric nearness problem is an interesting one, and it turns out that there's actually some really elegant algorithms for projecting onto that space. So one of them from 2004 is appearing in the machine learning literature, essentially just kind of iteratively updates violations of the triangle inequality and shows that it converges on this nice projection. A different problem, which is again kind of related, is something called Euclidean matrix completion. So here, the idea, remember that the input we assumed we had to the MDS algorithm was this matrix P, which was pairwise squared distances between a bunch of points embedded in Euclidean space. But what if we only have some subsample of the elements of our matrix P, and we want to complete it? We want to essentially find a dot product matrix, or equivalently a pairwise squared distance matrix, that has the prescribed entries that we care about, maybe just in a least square sense in case there's some noise, and then just fills in the rest under the assumption that our matrix is Euclidean. So here's one way to solve this. This goes back to 1999, and it uses essentially a convex optimization technique. So here H is a matrix of zeros and ones, with a 1 anytime our matrix P naught has a useful distance in it and a 0 otherwise. G is a gram matrix, just like we defined in our previous lecture, but now G is our unknown. And P of G is the mapping from gram matrices to pairwise squared distance matrices. So if you recall from our previous lecture, P is actually a linear map. Right? So if you think about the objective, what it's saying is essentially, okay, so P naught is a bunch of squared distance values. And then every once in a while, there's a missing element, in which case h is 0. So it's going to zero out that term in the Frobenius sum. And I'm trying to basically bring P of G and P naught as close to one another in the entries where I have interesting information. And the reason that we want G to be a semi-definite matrix, that's what this crazy inequality sign here means, is that, well, we know gram matrices are semi-definite because they look like X transpose X, right? And so that's the basic conceit here, that we look over all possible gram matrices for the one whose corresponding pairwise distance matrix looks the closest to our input data P naught. So I could like run this technique and then run the MDS to get my embedding, for example. Yet another technique is called maximum variance unfolding. And this one takes a little bit more picture drawing to get some intuition for what's going on. It's kind of a fun SDP, or semi-definite programming formulation, so I thought I'd spend just a minute kind of illustrating the logic here. So the basic problem in maximum variance unfolding is that, again, we're given some distance values, right? So we have some triplets. Oops, this pen is misbehaving. So we have some triplets of the form ij, d naught ij. The idea here being that I have a big collection of points, and between point I and point j, I know that their distance should be d naught. Okay, and my task here is to find the embedding of my data that respects these distances exactly and goes into some Euclidean space, hopefully of low dimension. So I know that if there are endpoints, I can always embed, assuming that the distances are correct, into n-dimensional Euclidean space, but maybe I can do better than that. And again, this is with hard constraints. So I'm thinking of my distance values here as actually being reliable. So here's the intuition for maximum variance unfolding. Let's say I have a really boring data set, which consists of 3 points. Okay? And moreover, I know the distance from point 1 to point 2, and I know the distance from point 2 to point 3. Okay, so I know the lengths of these 2 line segments. But what I don't know is the distance from point 1 to point 3. Okay, so this is a pretty straightforward setup here. So what do we want to find? We want to find an embedding of these 3 points given these 2 distance values. But of course there are many, right? I could draw an entire circle worth of locations, and all of these would respect my input data. But here's the kind of clever observation in maximum variance unfolding, which is to say, okay, well, in the lack of other information about my problem, I might as well get kind of the lowest dimensional embedding I can get. And thinking about this point as kind of turning about a hinge here, what do we see? Well, this data looks 2-dimensional if my hinge is any angle other than 180 degrees. But if I put my hinge straight out, so this angle is 180 degrees, well, now my data is a line. Well, lines are lower dimensional than 2-dimensional configurations of 3 points, so that's somehow desirable. And one way to express that as an optimization objective is to maximize the variance of these 3 points. So here, if my unknown embedding is a set of points y, then I can write the variance of my set of points y as the following. 1 over 2n, the sum over all pairs I and j of the distance from yi to yj, like that. As a sanity check, one thing that's easy to see here is, of course, the variance is 0 if all the y's are the same, so at least that kind of agrees. But you can check that this is really the variance in the usual statistical sense quite easily. And one thing you can find is that over all configurations of these 3 points, the one that maximizes the variance of every pair of points, including from 1 to 3, is the one that lays them out on a straight line as I've drawn here. That makes sense, right? Because, for example, if I hinge the point the other way, then this dotted line here is going to have a very short distance. And so I might as well kind of move it as far away as possible. This is related to a notion in architecture, actually. Sometimes they call this tensegrity, it's just a fun Google search term. It involves, like building structures by prescribing some distances and letting other ones maximize and minimize and so on. I'm not an expert in this kind of a problem. But in any event, in the maximum variance unfolding, we say, okay, I'm going to prescribe the lengths of some distances between points, and I'm going to try and find embedding of everything else. And the way that I'm going to do that is by maximizing the variance of my embedding. Okay, so now we're going to do a little bit of algebra. So in particular, okay, so we see a squared expression, so we can't help but expand the square here and say, okay, well, this is equal to 1 over 2n, the sum over ij. How many times have I written this in this class? The norm of yi squared plus the norm of yj squared minus 2yi dot product yj, of course. And now I can write this expression in a very different way. So notice that the first term and the second term, like for the first term, there's an index I but not an index j. So I gain a factor of n over the sum over j. So this is in effect 1/2 times the sum of the norms of the yi's. This is 1/2 the sum of the norms of the yj. So if you put those together, then I get that this is the sum, the norm of the yi over I, indexing that second term over j. And the second one can be written in kind of an interesting way, which is the sum over I of yi dot product the sum over j of yj. Hopefully you can see that, right? Because here this is a sum over all I and all j yi dot yj. So I can kind of factor it this way. Okay, so now, as with many of our embedding algorithms, since we only care about distances, we can safely assume that in our unknown embedding, we want that the sum over I of yi is equal to 0. We've justified that before. So in effect, that makes the second term 0, and what we're left with, is just the first one. So again, if we define the gram matrix, as always, to have entries g, I, j is equal to yi dot yj, then this first term here ends up being the trace of g. Okay, so maximizing the variance of our embedding y is the same as maximizing the trace of the gram matrix. So if you take a look at our maximum variance unfolding optimization formulation here, you can kind of see what it's trying to do. So the objective is trying to maximize the variance of the embedding of our data. The first constraint is saying that gram matrices have to be semi-definite because, again, remember that like the gram matrix is y transpose y or y transpose, depending on how you wrote your y's. The second constraint should look familiar. Oops, I'm noticing that there should be a square on the right-hand side. Maybe we'll fix that really quick. All right, fixed through the magic of video editing here, which is essentially the, remember there's the map from G to P, which takes the gram matrix and gives back the squared pairwise distance matrix. So the second constraint here is saying that the distance squared between I and j is exactly d naught squared, now that I fixed the right-hand side. Sorry about that. And then the third constraint is just the y summing up to 0, right? So that's basically it. And so, well, what we do typically, we'd have a fourth constraint, which is that g is equal to y transpose y. And we just drop that constraint and optimize for the semi-definite matrix G directly. And then what you can find is that when you take the eigendecomposition of G, or equivalently the Cholesky factorization actually, either one will give you an embedding that satisfies your pairwise distance constraint, which is pretty nice. And then sometimes in common practice, you again cut off some of the low eigenvalues of G to get an even lower dimensional embedding. So maximum variance unfolding, again, the basic point here is we have some triplets of distances that we trust. We want an embedding into Euclidean space, so we write it down as a semi-definite program, which maximizes the variance, which basically takes these hinge structures and wants them to be one-dimensional if it can. In general, it's trying to kind of inflate our points and push them as far away as possible. We can write our entire optimization problem just in terms of the gram matrix. So we do that to get a convex program. And then from the eigenstructure of G, we can recover our embedding. Covered that kind of quick, but this is mostly just, part of our grab bag of fun extensions. So let me clear out the board again. Okay, so this is just the tip of another iceberg. There are so many challenging computational problems in this space, even if we're given distances that are 100% accurate. So, some of the ones that I've listed on the slide here are things that you could think about. Some distances, may not be embeddable in a given Euclidean space. So you could ask whether your data is embeddable at all. One of the really tricky challenges, which is the second point here, is the idea of intrinsic dimensionality. So oftentimes in manifold learning, we talk about our data as cutting out some low-dimensional manifold embedded in a higher dimensional space. But there's often a parameter in these manifold learning algorithms, which is the dimension of the manifold. I think a totally reasonable and actually quite challenging question to ask is, given a big cloud of data points, what is the intrinsic dimensionality? Or even, is there a chance that this data is sampled from a manifold? Sometimes called the manifold hypothesis. Is quite a challenging problem. A different question you could ask related to embedding is whether two metric spaces are isometric. So can I embed these two things in the same domain, or can I embed one metric space onto another? This is a famously NP-hard problem, right? This is basically related to graph isomorphism and these sorts of things. You could ask how similar two metric spaces are in the case where they're not exactly the same, or even some really exotic things like, what does it mean to take an average of two metric spaces, which actually does come up in some applications. Unsurprisingly, a lot of these embedding problems are NP-hard. So the algorithms that we've derived in our lecture often work well in practice, but it can be a little bit hard to prove a whole lot about them. So for example, this paper shows that if I want an embedding of data that minimizes a particular notion of distortion involving L1 norms, this is an NP-hard problem to solve, and that's sort of unsurprising. Now, for the last little part of our lecture today, I thought I'd call out a related research area in machine learning that's quite popular, and this is an area called metric learning. And this is the basic idea that it's often desirable or valuable to learn a distance metric on a data set. And there's so many different settings for this problem, right? So for instance, I think a classic example is images. So images are maybe n by n grids of pixel colors. A famously bad distance between two images is to just subtract the pixels and square the differences in their colors. That certainly has nothing to do with the semantic content in the image, and even it turns out perceptually it's not a very good measure. And so maybe what you do is you start asking people like, here's a big data set of pairs of images, tell me which pairs look similar, have similar content. And then I might go back and try to learn a distance metric that reflects people's notions of similarity and dissimilarity. So this is a very popular problem, and one that many, many, many machine learning problems try to tackle. There's so many different approaches out there that I thought I would just kind of highlight in, a very naive, like spend 10 minutes on a whole research field kind of sense, some of the big ideas. So there are at least two very typical approaches to metric learning. One would be to learn the distance metric function directly. So maybe you have a parameterized version of the function d. So a very simple one is something called the Mahalanobis metric, which, as given on the slide, is very simple. You just have a semi-definite matrix A, and this is just some kind of Euclidean distance, but with an A that can give your data some anisotropy. In fact, if you factor A, then you can show this is the same as basically applying a linear map to your data points. Or the more popular approach these days is to just learn an embedding of your data directly into another space. So the second one has come with many different names over lots of different time. In some sense, this is like learning a kernel, depending on whether you learn the inner products between your embeddings or the embeddings themselves. In machine learning, sometimes we call our mapping from data into some space a feature vector. Now here I've written on this slide that this should be, an Rn. Lately, actually, an interesting trend has been to learn mappings of data into other spaces. So for example, trees embed well into hyperbolic space. Essentially, so if I have data that looks like tree-structured graphs, then it actually may not make sense to use Rn as much as one of the model hyperbolic spaces. The reason for that is that trees branch, and somehow the potato chip structure of hyperbolic space, which has more and more area as we move out from the center, is useful for data that branches out a bunch, which is kind of funny. But in any event, the typical feature vectors are in Rn, but they don't have to be. So anyway, once you've decided on the way that you want to map your data or embed it, the next thing you need is a loss function. There are many choices. I've referenced a survey on the bottom that I encourage you all to page through, which is actually a really nice and kind of relaxing, fun read on metric learning. It comes before some of the deep learning craziness that we have these days, but predicts basically the same loss functions that those folks use now. There are many different ways that you might learn distance metrics given very weak signals as opposed to the strong signals we've considered earlier in this class. So a very typical thing to do is to assume that we have sets S and D, which stand for similarity and dissimilarity. The idea being that I have some pairs of points that I know should be close to each other. In my unknown distance metric, I know that some pairs of points should be far away, and I'm going to optimize for a distance metric with that property. Once I have those sets S and D, there are many different things I could do. So for example, I could have bound constraints, like every pair that's inside of S has to be closer than U, and every, U standing for upper bound. And every pair of points that's in D needs to be distance at least L away from each other. And then I could optimize, for example, for a Mahalanobis metric that satisfies these constraints. This is the sort of hard constraint version. There's also a hinge loss version, which says that I'm just going to penalize distances that are big when points should be similar, or I'm going to penalize distances that are small when points should be dissimilar. Hopefully I phrased that correctly. Or these days, one of the particularly popular ideas is to use a triplet loss, where you say, I'm going to take a pair of similar points and a pair of dissimilar points. And what would I like? Well, I'd like that the pair of similar points has a small distance, and the pair of dissimilar points has a large distance, and so maybe I cook up some metric that tries to measure that sort of thing. And so in that case, maybe I even add a parameter alpha, which is the margin between these two. So there's so many different examples of metric learning and embedding out there in the machine learning literature. One of the best known ones and really intriguing ones is something called word-to-vec. We're not going to cover the details in this course, but word-to-vec is kind of funny. It basically builds on the loss functions that we've explained and some variations thereof using Kale divergence. And the idea is to learn an embedding of the English dictionary, or whatever dictionary, into Euclidean space. So every single word in some corpus of documents gets assigned a different feature vector, with the property that words that are similar in the sense that they appear nearby in lots of documents should have nearby embeddings. And word-to-vec is this extremely, extremely popular idea because it allows you to put geometry on the space of words. One nice thing is if you don't want to fight with running the code, you can actually just download the word-to-vec embedding of the dictionary. So like you literally just a list of words and vectors. And now suddenly you have a geometry for your natural language processing application. One of the particularly intriguing aspects of word-to-vec, which to my knowledge is still a little bit unexplained, is that you can even do arithmetic in this space in like sort of a vector way, like Paris minus tower plus bridge equals London, that kind of thing. And somehow this structure arises from just pretty simple metric learning style objective functions and constructions. A different popular embedding technique, which has been around for a long time and still is widely used in the data science community, is something called T-SNE, or T-distributed stochastic neighbor embedding. This is an algorithm for taking high-dimensional data and embedding it into low-dimensional space. And in particular, we assume that the input and output data are both Gaussian, or rather are both Euclidean in nature. Although I think the input could be a distance matrix. That might be okay for T-SNE. In any event, the T-SNE algorithm is kind of interesting because its job in life is to try and find an embedding where the thing you care about the most is cluster structure. So like if there's a big clump of data points in your high-dimensional space, you want it to look like a clump in your low-dimensional embedding. If there are two clumps, you want them to be embedded as clump, but the relationship between them in your embedding is less important. T-SNE follows a set of 3 steps, which are kind of interesting. So the first thing that it does is it constructs a probability distribution on pairs of points from the pointwise embedding. So the way that it does that is by just using a Gaussian, like a bell curve. So you can see here, like the probability of j given I is just a Gaussian of the distance between I and j. The prior, like the size of that Gaussian, they call that the perplexity or variance of your T-SNE embedding. Then you symmetrize, so you just average your probabilities with a transpose. And then the third thing, which is kind of interesting, is now you're going to find an embedding of your data. These are the y variables on the right-hand side, and the y variables are in a lower dimensional space. And we constructed a probability distribution on pairs out of distances. And what we're going to do is maximize the mutual information, or like the KL divergence, minimize the KL divergence between a new distribution, which is constructed from the embeddings of the y's. But the kind of magic sauce that goes into the T-SNE algorithm is that we use the Gaussian distribution for our high-dimensional data, and we use the student T distribution for the low-dimensional data. And we're trying to maximize the KL divergence, minimize the KL divergence between these two things. The reason for that is that the student T distribution is something called heavy-tailed. So here's a bit of intuition. So Gaussian or normal distributions, like what's shown in gray, they're very pointy. It might not look like it in this diagram, but the key point here is that all of the mass in the Gaussian distribution is kind of really centered close to the mean of that distribution. And then it drops to 0 very fast. If you take a look at like the Cauchy or the student T distribution, okay, it is a little more peaky in the middle, but then what happens is it's heavy-tailed, meaning the decay of this blue function to 0 is much slower, meaning that there's more mass kind of farther away. And so what that allows you to do, there's a cursive dimensionality issue when going from high to low dimensions, which sort of says that there's, big differences between small distances and large distances in high dimensions. It's hard to capture in lower dimensions. But by sort of allowing there to be heavy tails in your mutual distribution term, what you're doing is allowing large distances to get distorted more in the T-SNE embedding. And so here's like a very typical T-SNE embedded result of just some data set. In this case, I think this is the MNIST digit data set. You can see that there's like really nice clusters between different parts of your data. And so people doing exploratory data analysis really like this T-SNE technique because essentially it allows you very quickly to discover interesting cluster structure in your data. In fact, sometimes it allows you to discover cluster structure a little too well. So one thing that's well known about this T-SNE algorithm is that it wants there to be clusters in your data, even if there aren't any. And so depending on how you choose that perplexity parameter and some other ones in this technique, you can end up seeing clusters even when there's not actually interesting information. And this is sort of a common pitfall in some data analysis techniques out there. So a little bit of required reading if you're interested in this kind of topic is this How to Use T-SNE Effectively document that I've linked in the slides, which gives a nice kind of interactive guide to what can go wrong if you abuse the T-SNE technique. And of course, machine learning universe moves very quickly these days. The data science preferred embedding technique has moved on to another algorithm called UMAP, which has a lot of structure in common with T-SNE, but actually builds up a sort of simplicial, complex-looking structure on your data, and then uses T-SNE style embedding technique from that complex. This one's a little more challenging to describe mathematically, so we're going to defer on that, but I've linked to some interesting articles. In any event, hopefully what you guys get out of today's discussion is that oftentimes the embedding that we try to compute of a given distance metric may not need to preserve every possible pairwise distance. Maybe what we really care about is structure. So for example, that structure might be just distances that are in local neighborhoods, like what Isomap and LLE are trying to conserve. It might be some manifold structure, like what the surface parameterization techniques are doing, and so on. In addition to that, there are interesting structured learning problems that are even weaker than that. For example, in metric learning, maybe the structure is just that I know that some points should be somewhat nearby and other points should be far away, but I don't care about the exact distance value. And then I can start using things like those hinge loss objective functions we outlined toward the end of today's discussion. So this wraps up our discussion of distance metrics, both the forward problem of computing geodesics and the inverse problem of embedding and metric learning. When we continue next time, we're going to kind of embark on the next big unit in 6838, which is Laplacian operator. So with that, I'll see you next time.